that it can take and multiply or weight it by its probability, and you do for all possible outcomes, and you get the expected value of x. So, think about this. It can be 0, and that must be weighted by its probability. It's 1/8. 1 can happen in 3 out of 8 times. Okay? 1 is here, there, 3. The probability of getting a 1 is 3/8, and then you do this, and you get to the result that you have expected. In 3 flips, on the average, I'll get 1.5 heads. Okay? Now, there is a fundamental property, extremely important property of expectation. And it's illustrated here. Suppose that you have 2 random variables, x and y, and you add them. And you get z. Now, it just happens that, not just happens, but I will not prove it here, so take for granted or remember what you've learned before. The expected value of the sum is equal to the sum of the expected values. So this means expectation is a linear operator. Okay? So when you have 2 random variables, or 3 or 10, and you want to compute the average of their sum, you just compute the average of each one and sum the averages. Okay? So that's a fundamental property that we'll be using a lot. Now, the final thing that I want, and this some of you may not have learned, so that's an occasion to do that. It's the expected number of trials to success. Here's the problem. Suppose on each trial an event occurs with probability p. Think in a concrete way. For example, you toss a die and you're interested in the outcome. Look, the face that I see has 5 spots. We all know if the die is fair, the probability will be 1 in 6. Okay? When I toss it, I can get a 5 right away, or I may have to toss it twice or 3 times. On the average, how many trials do I need in order to get number 5, the face with number 5? Okay? There are many ways to compute this. Some people intuitively know what the result is. Let's prove it. And in this proof, we have one of those fundamental techniques of probability. We call it expectation by conditioning. We are going to condition on the outcome of the first trial. But I'm getting ahead of myself. Let's say that E is the expected number we're trying to find, okay? Expected number of trials until I get the event. Well, what happens on the first trial? Either I get the event or I don't. If I get the event, which occurs with probability p, then I only needed 1 trial. So E is equal to 1. What happens if I don't get, and that's the crucial step of the argument, what happens if I don't get the event? I didn't see the 5. Okay, this occurs with probability 1 minus p. But if that happens, the expected number of trials until I get it is just 1 plus what it was before. Okay? And that's the crucial observation. So I go back to square one because the probability is the same, the events are independent. So I can compute the expected value in the following way. Look, with probability p, I get the event. I'm just applying the formula you saw before. With probability p, I get the event, and then I only needed 1 trial. Well, with probability 1 minus p, I didn't get it. And in this case, the expectation just increased by 1. So I will spare you the algebra. When we solve this equation for E, we get 1 over p. Now, this, for many people, is highly intuitive because, for example, if you're interested in a coin, the probability of getting heads is 1/2. How many trials do you need before, on the average, before you get heads? Well, it's 2. 1 over 1/2. Okay, so you just take the reciprocal. And for the die, the expected number of trials before I see a face with the 5 dots is 6. It's 1 over 1/6. Okay? That's the end of this preliminary stuff. Now let's get to some interesting problems. Okay, let's try to find this one. On each trial, our rat chooses randomly one of the 8 arms of the maze. In probability, it's fundamental to have very clear thinking and define your variables carefully. That is, many times, half of the way to the solution. Lots of terminology, lots of symbols. If you control them, they will be your friends. If you don't control them, they get to be wild beasts, okay? And confuse more than illuminate. So, let T be the total number of trials needed to visit all arms. T for total, remember this. What is the expected value of T? How many trials, on the average, does this stat rat need to visit all 8 arms? Okay? We know one thing right away. It must be greater than 7. I will need at least 8 trials to visit 8 arms. So whatever answer we get must be bigger than 7. So here's the problem. What is the expected value of T? Always good to start with an example. Suppose that a stat rat visits the arms in this order. I have numbered them here, as you can see, and I have printed in red ink an arm that it has visited for the first time. Okay, so black means a repeat here. So the rat visited arms 2, 5, 3, they're all new. 3 is a repeat, so it's in black. So I keep going until I see all 8 arms visited. So when the rat visited arm number 7 here, it's printed with green. I don't know if you can see it. But then it has visited all of them. In this particular case, T was 15. So T is going to be a random variable. And we want to find its expected value. Now, this may sound like paradoxical, but we're going to use, that's another technique that we're going to learn here, or remember, we will use a historical but forward approach. As you can imagine, there is historical backward approach. We will use the forward approach. And again, in these probability problems, many times there is a framing way, a way to look at the problem that is the solution, basically. That's the key step, and I don't know how to teach this. Many times I don't get it. It's the way to conceive the problem. One good rule of thumb is divide to conquer. Sometimes I cannot figure out that expectation right away. So the idea is, can you break the problem in parts and figure out the solution to each one of the parts and then somehow combine? It's very vague, but that's where intuition and lots of training come to solve these types of problems. So the key step is this. We're going to define a new variable, and we call it x sub j. When you see a random variable with a subscript, we need to understand 2 things. What does it stand for? What's the subscript doing? So let's go by parts. What is x? X is the number of trials taken by the rat to visit a new arm. Complex definition, but it will help us in a moment. So, number of trials to visit a new arm. So what's the subscript doing? It's going to be a condition, given that it has already visited j arms. So, if your rat has visited j arms, how many new trials did it need to visit a new arm? Okay? Again, let's see how this works with a concrete example. Returning to that stat rat that shows the, whoops, I'm pointing to the computer, visited the arms in this order. Let's see how the x sub j, which is the key to the problem, is used. Well, before the first trial, the rat has not visited any arm. So j, the number of arms already visited, is 0, right? So on trial 1, the rat visited arm number 2. It's a new arm. So I just repeat it here. So x sub 0 equals 1. Again, what is x sub 0? Number of trials needed to visit a new arm, given that I had visited 0 arms. Well, I just needed 1. So x sub 0 is equal to 1. What about now, on the next trial? Well, j now is 1, because I've already visited 1. The rat chose arm number 5. That's a new one. So when the rat had visited 1 new arm, it needed only 1 trial to visit a new arm, the second one. So x sub 1 is equal to 1. Is that okay? Well, we could go one more round. Again, it visited a new arm, so x sub 2 means when the rat had visited 2 arms, how many trials did it take to visit a new arm that had not visited, of course. So now, more interesting is a repeat. What happens in a repeat? Notice that when the rat had visited 3 arms, the next trial visited arm number 3. Well, this is all, so I keep counting. I keep counting. So x sub j is going to be a counter. Okay? Now, on the next trial, whoops, repeat it again. So this is not a new arm, so I just keep counting.